Here, I'm going to follow up on my discussion of spectral characteristics of materials. I talked about vegetation before. Today, I'm going to talk about soils and water. I'm going to talk about how those materials um, reflect or not, how they interact with incoming sunlight. So I'm going to skip the sections in the book on thermal energy and microwave, kind of active energy. We're going to touch upon those both later in the semester, and they're they're different enough that I don't know if it's best to get into them at this point, so to speak. I will start by looking at our spectral black body figure. So this figure 2.5. Vertical axis is showing the radiant excidence from different materials, um, how that varies by wavelength. That's the horizontal axis there, wavelength, and then by temperature of the object themselves, and that's the different color curves here. We saw that yellow curve was the sun, which has a surface temperature of about 6,000 Kelvin, and that this maroon curve is the surface of the Earth, about 300 Kelvin. Now, I found another version of this figure right here on the right, showing the same thing, except it has a few more labels. So the sun is labeled, Earth is labeled, things that are colder than the surface of the Earth are labeled. So they would kind of just be on a continuation of that, with lower radiant excidence and a longer peak wavelength. But one thing that caught my eye that I think is worth mentioning, because maybe it's helpful for understanding this, is the 800 Kelvin red hot object. So something that's hundreds of degrees hotter than the surface of the Earth, but still something that we are familiar with. We're not thinking the surface of the sun. Oop, excuse me. So this 800 Kelvin object has kind of a peak radiant excidence of wavelength, I don't know, that would be 7 micrometers. So kind of somewhere just shy of what we consider thermal infrared, but kind of beyond shortwave infrared. That's the peak value. But what's interesting is what happens, or what the curve looks like when it descends on the shorter wavelength side. So it gets to a point where there's little, but there might be some energy emitted at a wavelength of about 0.7 micrometers. So that's just short enough to be visible. And that is the red area of the visible spectrum. So if an object is hot enough to emit energy according to that function, it will be at some temperature, call it 800 Kelvin, could be 805, I'm not sure. But at that temperature, you'd start to see some energy emitted from the object that you can see with your eyes. If it's 700 Kelvin, you get close enough to it, you will feel it being hot. But only at 800 and above, hotter than that, will it actually generate color. Will it become red? So that's just a little bit of review, another figure, just to help you maybe explain how the temperature of an object influences the amount of energy that it's radiating, as well as the wavelengths of that energy. Moving on to another review slide. These are the kind of physical model of electromagnetic energy interaction with Earth material. And in the figure here are leaves, and the model applies to leaves, but it applies really to everything. So of the incident energy, that phi 1, or phi iota, I guess, if I'm reading it right, the yellow line, of all the energy that's coming in and is incident or interacting with the leaf, some will be reflected, that's the red arrow, kind of subscript R there. Some will be absorbed, kind of raising the energy state, the temperature of the leaf, black, and some will be transmitted through. So if you're under a tree in the middle of the day, um, you're in the shade, but you can still see some light coming through. It's not like you're under a roof. So those are the kind of the three possibilities, these reflected, absorbed, transmitted energy, of what can happen to the incident energy. And those three components summed up will equal the incident energy. Reviewing again, here are some spectral reflectance signatures for representative Earth surface materials. So what this is showing, vertical axis is a percent, so ranging from 0 to 1 essentially. It's a fraction of the reflected radiance to the incident. So if we go back to our plant slide, it is the red arrow magnitude divided by the yellow. So the red is always going to be smaller than the yellow because we're not taking into account absorption, and transmittance. So we can plot all these values on a scale of 0 to 100. Typically, you might see a maximum value here just to highlight the greatest range of variation of the profiles. And note how the behavior of different materials, really in the portion that's reflected, varies according to the wavelength of light. So those objects, to jump back, whether it's coming from the sun, the earth, or some red hot object, those objects are creating or are generating energy across a continuous spectrum. So the peak wavelength of light from the sun might be yellow, kind of right there, but its sun's also generating blue light or near infrared light or thermal light. So we can distinguish these different Earth surface materials, kind of representative. You can think of them as being idealized too. Oops. Water, vegetation, sand, concrete, snow. We talked a little bit about vegetation, this kind of green curve here that I'm tracing out. And today I said I'd talk about some soil properties. Really, I'm going to be comparing soils to vegetation, kind of photosynthetically productive vegetation. Also do that for water too, this kind of blue curve down here. So soils taken as a whole are kind of characterized by having very low transmission of energy. And that kind of makes sense. The light doesn't really penetrate the soil in the same way as it could pass through a leaf. And so of the energy that's coming in, if you accept that very little will be transmitted through, you're talking either absorption or reflection. So often, for a lot of soils, they may have very high reflection. And I think the example in the last slide here of sand shows that. So in all of the wavelengths we see, sand is more reflective than green vegetation, even the near infrared, which we usually think of as vegetation being highly reflected in this region. Now, sand is just one type of soil, though. I'll skip ahead to this third one. Like we see with vegetation, there's a variation in reflectance across wavelength due to a number of factors. And these can be due to factors at the molecular scale, kind of the presence of iron and silica. They could be due to factors at the scale of the sand grain or the silt, the clay, the grain size. So as with vegetation, it's I- Your your within class variation. I'm using that term within class to talk about why different areas of soil might behave differently with respect to the light. That within class variation can come about due to a number of circumstances or factors. The other thing I mentioned here, it's anisotropic. Anisotropic means that it will interact with light differently um, on the basis of the direction. So that could be the orientation of the sun, the material itself, so kind of the grain, and the way the sensor's viewing it. And so isotropic materials would reflect light in all directions, the same way, or similarly. Anisotropic means there's great variation in that, or there can be. Because of this, the kind of anisotropic properties, which could come down to the crystalline structure of these grains, the you might observe a wide range of reflectance properties or characteristics of a material that's actually the same. And we'll kind of look into that with water too. Kind of we saw that in one of the figures. What are all the reasons why your observations may vary? So for soils, even things like the directional orientation of the sensor, the sun, and the material can lead to differences in what is observed. And that can be a challenge because those differences in observed energy may not actually describe differences that are important to you as someone who's studying the environment. And then finally, unlike vegetation, we see slower change through time in these properties, typically. With vegetation, you can see variation within the day, certainly within a growing season. For soils, um, typically you would not. You certainly could. I mean, there are definitely disruption events. Erosion in certain areas does happen relatively quickly, but those are to some degree the exception. Going to water. Water has very high transmission absorption of energy and very low and limited reflectance. And so by low, I mean a small percent of the incident energy is reflected. So you see here the vertical axis goes from 0 to 10 only. In limited, I mean in certain wavelengths, you're not going to see any reflectance. So here you'll also note that the horizontal axis, wavelength of light, runs only within the visible into a little bit of the near infrared. And if you look at the profiles here, turbid river water with more suspended solids in a solid line, clear lake water, a lower amount of suspended solids as a dashed line. The clear lake water really doesn't even leave the visible. Now you can see here by the kind of use of turbid water as kind of a category of interest, water is kind of interesting in remote sensing because when it's studied, often it's the sediment in the water, it's the phytoplankton maybe in the water that may be the focus of the study. So you look at water, but you're interested in what's in the water, what the water contains. But also, water is it plays a big part in a lot of remote sensing analysis in terrestrial areas or in the land because the amount of water contained within soil, within vegetation, say, can really change how those materials are observed. So here, this is a spectral space. So vertical axis reflectance up to 70%, wavelength is horizontal axis, and all these signatures are different surface areas. And I'll just draw attention to here to the contrast between dry soil and wet soil, where these two, this kind of, I don't know what you call that, teal signature and the more olive green one here. They're similarly shaped, but you see the dry soil is reflecting quite a bit more across nearly every wavelength than the wet soil. So in general, water places a downward pressure on or exerts a downward force. It drags the profile down toward lower reflectance. And so here's just a slide to sum up some points that I tried to set the stage for in other slides, but maybe not stated them explicitly. So the first here, for any material, expect that the variation of reflectance with wavelength, so really the fact that there is a spectral curve in this two-dimensional space, it's due to a number of factors at a number of scales. So here in this kind of figure 2.11, 2.11, for vegetation, we see the general explanation is that leaf pigments, their photosynthetic activity, explain visible reflectance. Cell structure explains the high reflectance in near infrared, and water content explains really how much is reflected in the shortwave infrared. Now that's, it may not be a nice, neat, non-overlapping, exclusive categorization, but just recognize that these different factors are used to attribute behavior at different ranges of the same spectrum. I mentioned that, okay, there's a lot of research into understanding how subtle differences at a number of different scales, kind of the molecular, the cellular, the larger, explain these differences. With that, it's just a nod to the need for this kind of outside additional context familiarity in order to understand specific causes for observed variation. It may require work beyond what the satellite sensor can show you, for instance. And it may not even be possible to disentangle some of these. That points to another thing, second point. What the sensor observes, and we're going to get into this a little bit in topic 3 as we start to think about the real systems for observation, how these kind of principles really, which we've been focusing more on the materials that are being observed, how these observations are also reflecting the way we observe. So what these spectra are, they're not exactly what the sensor sees. So they're more idealized, the output of detailed on-the-ground research. So every observation from the sensor is going to be mixed. We see that a little bit here with, okay, what happens when there's more or less water content in the grass or in the soil? But as I mentioned before, we're kind of talking about within category variation. When we categorize on the basis of between category difference, so between category meaning the difference between wet and dry grass, soil and water, for instance, we should recognize that because observations are mixed, what we call dry grass may vary itself, hopefully just a little bit. Hopefully it's something we can constrain, but it's going to vary. There's no perfect repeated everywhere profile for a given category of interest. And so the challenge is identifying and interpreting the differences in our observations with respect to the conceptual differences of meaning. And so what I mean there is just setting up what categories are we interested in, whoever made this figure, interested in wetlands, green and dry grass, soils. Think about what we're interested in and whether or not we're able to really disentangle it based on what we can see. Going back to here, figure 2.9. So these are all the reasons that the data from the sensor may vary. It could be down to atmospheric components, land cover variations, so that could be difference in the actual materials, soil and geological substrate, so difference in physical materials, but not even the ones we're interested in. Say, in this figure, I think, for the purposes of the figure, we're just interested in the vegetation. Could come down to the changes in the sunlight, or with terrain, slope, and aspect, how sunlight, materials, and the sensor are spatially arranged. So some of those are going to be important to us. All of these might affect the data. Some of them are going to be important on the knowledge that we want to generate as well. And then finally, something I posted on Blackboard is just a feature I saw New York Times website. It must have come out today, yeah, September 2. It has to do with analyzing aerial imagery and characterizing kind of variation in color and how that lines up with presidential election margins in 2016. It's not anything that you need to know about for this course. I included it as just an example of how remote sensing is something that it's kind of a technical discipline. It's something that you need to kind of study, have a new frame of reference or a new way of seeing things to really do on a day-to-day basis. But it might have things that are of wider interest. So I just included it as an example of that. And as I say, I'm not even so sure it's providing that much additional benefit beyond what other data could give you. But just so you know how to place that, I'll mention it now.